Welcome to Everyday Mathematics. Today we move forward to quarterfinals number 2 and we look at problem number 1 in that quarterfinals and then problem number 2. So these are interesting problems. Let's see how we may be able to solve them. I do like the second problem particularly, but both problems are very interesting. So let's see how we may be able to solve them. So problem number 1, a definite integral of from x equals to 0 to x tending to infinity of 1 over x to the power 6 plus 1. So the important thing here for us is to know that x to the 6 plus 1 is the same as 1 plus x squared times x to the 4th minus x squared plus 1. Okay? So that's that. And so our integral 0 to infinity of 1 over x to the 6 plus 1 is the same as the same integral from 0 to infinity of 1 over x to the 6th over x to the 6 over x to the 6 plus 1 over. So we've divided both the numerator and denominator by x to the 6. So this becomes 0 to infinity of 1 over x to the 6 over 1 plus 1 over x to the 6. And we can say let u be equal to 1 over x such that du dx equals to 1 over x squared, and so du would be equal to negative dx over x squared. Okay, and then when x equals to 0, u would tend to infinity. When x tends to infinity, u would tend to 0. So 6 over 1 plus 1 over x to the 6th is the same as 0, infinity, 1 over x to the 4th over 1 plus 1 over x to the 6th, then dx over x squared. So this here I have gotten from here. And so we get 0 u to the 4th over 1 plus u to the 6th negative du. And so this negative here allows us to swap the limits, right? So this becomes over 1 plus u to the 6th du. In other words, the integral of is equal to integral of dx. This is an important arrival or derivation. Therefore, our original integral is equals to a half. Okay, and that means that we have half 0 to infinity 1 plus x to the fourth over 1 plus. Okay, but we saw that x to the sixth plus 1 equals to 1 plus x squared, x to the fourth, x squared plus 1, which means that our integral equals to a half infinity, and this here is the same as this part, x4 minus x squared plus 1 plus x squared, all over 1 plus x squared, x to the fourth, x squared plus 1. So which is equals to a half, 0, infinity. We have x to the fourth minus x squared plus 1 over 1 plus x squared, x to the fourth minus x squared plus 1. And we see this and this cancel, plus a half x squared. We could express this same thing, but we can also say this is the same as that. So here we say 1 plus. Okay. So this is the same as a half infinity 1 over 1 plus x squared plus a half. This is 0 infinity, 0 to infinity, x squared over 1 plus x cubed squared, yeah, dx. So this here is the same as a half arctangent of x, 0 infinity, plus a half 0 to infinity, and this here is the same as a third, the derivative of x cubed, right? And we can say that now we can replace this as u, and this is as u. So we have half arctangent of x, 0 infinity, plus a half, a third. And so we are replacing okay, so this is a half. Let me just write up everything. So we say limit as x tends to infinity of arctangent of x minus limit 0 arctangent of x plus a 6 arctangent of u, 0 infinity. Here we have half times pi over 2 plus a 6 times, I think this also would go to pi over 2. And so this is pi over 4 plus pi over 12, which is 12, 3 pi plus pi, which is 4 pi over 12, which is pi over 3. Okay. So, and so the solution to our problem is 0 to infinity of 1 over 1 plus x squared is equals to pi over 3. And that is our answer. So problem number 2 is the definite integral from x equals to 0 to x equals to a half of the natural logarithm of 1 minus x over x. Now, this requires one to know what this function, dilogarithm function, is all about, right? But I'm not going to try to use that. I will try to use the basic identities of natural logarithm of 1 plus x being equal to, from n equals to 1 to infinity, of negative 1 n minus 1 x to the n over n. So that's identity number 1 I would like to use. Okay. And the next identity that I would like to use is and this is what we call the Bessel problem. Okay, this here is Taylor's expansion of the natural logarithm of 1 plus x. To be very precise, this is what we call the Maclaurin's expansion of natural logarithm of 1 plus x. Anyway, so this is the building blocks that we're going to use for this problem. One thing I'd like to also do for this problem is maybe let's use let's re-express this problem as follows. 1 over x is the same as the derivative of natural logarithm of x. Okay, and then if we use integration by parts, we'll see that this is the same as natural logarithm of 1 minus x, natural logarithm of x, okay, 0 to half, okay, minus integral from 0 to a half natural logarithm of x times the derivative of natural logarithm of 1 minus x. Okay. That brings us, so here we will say limit as x tends to a half of natural logarithm of 1 minus x times the natural logarithm of x minus limit as x tends to 0 of natural logarithm of 1 minus x times the natural logarithm of x, okay, minus, so this becomes plus, from the derivative of this, 0 to a half of natural logarithm of x over that. Okay, I will leave this as an exercise for whomever to derive what is the limit as x tends to 0 of the product of natural logarithm of 1 minus x and log of x. So we'd come to a point where we had limit as x tends to a half of the natural logarithm of 1 minus x logarithm of x minus limit as x tends to 0 of natural logarithm of 1 minus x times the logarithm of x, and then plus integral from 0 to a half of natural logarithm of x over 1 minus x. Okay, and this here tends to 0. And this here tends to log of half, log of half. Okay. So we'll soon see that this is log squared of 2 plus, we're going to try and substitute for things here. We would say let u be equal to 1 minus x such that du dx is equal to negative 1, and so du negative would substitute for dx. And then as x tends to 0, we would have u be equal to 1. So we have 1 here. As u tends to a half, we would have a half. And then log of x would be 1 minus u over u. And then we have negative u. This negative here allows us to flip the limits. So we have plus a half to 1 of, we can decide to take things back to the x domain, and that is it. Okay, so if our original integral were I, that has taken us to log squared of 2 plus the integral from half to 1 of log of 1 minus x over x dx. If we add both sides with I, we have log squared of 2 plus the integral from 0 to a half of log of 1 minus x over x plus integral from a half to 1, which is this one, and this here happens to be I, this here is I, and then here is log of 1 minus x over x. So 2I is equals to log squared plus 0 to 1 log of 1 minus x over x. So this is a very good problem to solve now. So we come to a point where we have 2I is equals to the square of natural logarithm of 2 plus 0 to 1 of the natural logarithm of 1 minus x over x dx. And we can re-express 1 over x to be the derivative of natural logarithm of x. And we could try and rewrite this one. I want it to be a slanting one. So we have square of log of that, and we're going to use integration by parts. So we have a product of this and that first. We have log of 1 minus x, log of x, 0, 1, minus minus, the derivative of this guy here becomes negative, so we have plus 0, 1 log of x over 1 minus x. Now this enterprise goes 1 as x tends to 1, this goes to 0. As x tends to 0, this goes to 0. So this entire enterprise goes to 0. So we are left with the integral of from x equals to 0 to x equals to 1 of that. Now we know that x to the k summed from k equals to 0 to k equals to infinity equals to 1 over x when the absolute value of x is less than 1, and this holds in the domain of interest. So 2I equals to log squared 2 plus integral from 0 to 1 of natural logarithm of x summation from k equals to 0 infinity of x to the k. And we can say this is, we can pull the summation out, integral 1 of log of x times x to the k. Again, integration by parts. So we have squared of log of 2 plus summation from k equals to 0 to infinity, integral 1 and log of x times the derivative of x to the k plus 1 over k plus 1. This. So we have log squared 2, and this is 2I equals plus summation from k equals to 0 to infinity of 0 to 1 of log of x, derivative of x to the k plus 1 over k plus 1 dx. And this is square of log of 2 plus 0 to infinity of first the product of log of x, xk plus 1 over 0 to 1 minus xk plus 1 over derivative of log of x is 1 over x from 0 to 1. Now here, limit as x tends to 1 on the upper side, this goes to 0. As x tends to 0, it goes to, so this entire enterprise goes to 0. So we are left with the square of log of 2. This minus comes out, so minus the summation from k equals to 0 to k tending to infinity of the integral from x equals to 0 to x equals to 1 of x to the k over k plus 1. Okay, so 2I is equals to the square of log 2 minus summation from k equals to 0 to infinity of 1 over k plus 1, 0 to 1, x to the k, and over k plus 1. And then we have kx plus 1 over k plus 1, 0, 1. And as you can see, let's just use this square bracket here. Limit as x tends to 1. We have 1 over k plus 1 on the upper side and 0 on the lower side. So we have infinity of summation of the square of, okay. And we can, since we have come to a point where we have 2I being equal to the square of log 2 minus k equals 0 to infinity over 1 over k plus 1 squared, We can start from k equals to 1. So 2I is from k equals to 1 to infinity of 1 over k squared. And this here is our Bezoar problem. So we have 2I is equals to the square of log 2 minus pi squared over 6. Divide both sides by 2. We have log square of 2 divided by 2 minus pi squared over 12. And that is our answer. So we can rewrite our integral the solution. We have 0 to a half of natural logarithm of 1 minus x over x is equals to the square of natural logarithm of 2 over 2 minus pi squared over 12. And that, ladies and gentlemen, is our answer.